Okay.
Yeah, you could get started.
Okay. Hello, everybody. Welcome back to our chemistry seminar. Today is our third session, and we have Vanessa Seifert as our speaker today. So Vanessa Seifert is a Marie Curie postdoctoral fellow at the University of Athens and a visiting fellow at the University of Bristol. Her background is in chemical engineering. She completed a master's in philosophy of science at the London School of Economics and a PhD of philosophy at the University of Bristol. Currently, her work focuses on the metaphysics of chemistry, the relation between chemistry and quantum physics, and scientific realism. Recently, she published her first book entitled Chemistry's Metaphysics. She's a regular writer for Chemistry World magazine and Jargonium. Please welcome Dr. Vanessa.
Hi, everyone. So should I start?
Oh,
I
yeah,
only
of
see
course.
you. Okay, perfect.
Right. So we have to improve this next time around
Yeah.
because
No, it's like,
we have
no,
a
no, it's
camera.
fine.
Yeah, we have a camera in the room, but I don't know how to get it working.
Yeah,
So
yeah.
I
yeah.
didn't say it as a bad thing. It's just it feels like I'm talking. No, it's a good thing. So I'm not nervous. Okay,
You know
so I'm
what? I'll
going
give
to
you the
start.
expressions of the class.
Yes, exactly. Okay, so thank you for inviting me. I'm very excited when I give talks, especially to chemists and prospective chemists, of course. Today, I've decided to talk a little bit about the field philosophy of chemistry, um, and because I have well, I don't want to make this assumption without any justification, but in case this is the first time you come across philosophy of chemistry, I wanted this talk to be more of an introduction of how philosophy talks about chemical issues and what sort of chemical topics philosophers grapple with. Right. So let me start first with a general introduction. Philosophy of chemistry um, technically is a subfield within the more general field, which is called philosophy of science. Philosophy of science is a discipline that is both old and new, in the sense it's old because people have been asking philosophical questions that relate to science for a very, very long time. We can track it back to Plato. I have Plato here, Plato and Aristotle. And even, famous scientists centuries ago would raise questions that we would deem today as philosophical. And that's why I have Isaac Newton here as an example. So, for example, for philosophers of science, Newton is very famous for getting into the debate about the nature of space-time. And there was a debate between him and Leibniz about whether space is absolute or relative, whether space that is determined by the things that are contained with it, or whether it exists independently of anything, any sort of matter being within space, right? And this was a huge debate back in the day, and it's a philosophical debate that still persists in the field. But of course, also it's a very new field as well, and that's why here I have the president of the Philosophy of Science Association that is based in the States and is like the one of the two biggest philosophical associations in the world, Michela Massimi. So a lot of women as well nowadays that are working on philosophy of science. But institutionally, formally, philosophy of science was created in the 20th century. And there's a reason for that. Well, because many great scientific advances happened at the beginning of the 20th century, especially in physics, right? We have Einstein with the relativity theory, we have quantum mechanics, we have biology a lot growing in the 20th century. And so there was a lot of, new material and new knowledge that was produced that inevitably led to the creation and raising philosophical questions. Apart from that, or rather, in addition to that, all these great scientific advances also created a lot of confusion because classical concepts had to be reinterpreted. space-time, again, being one of the most, paradigmatic examples. But also the atom, to bring you something closer to chemistry. Chemistry's atom became unified with how physicists thought of the atom in the 20th century through quantum mechanics, and they realized that they were talking about the same kind of thing, right? And all these advances created, a need to understand better classical concepts, or even to reinterpret them in a way that, wasn't scientists hadn't gotten used to before that. So there are four main topics, or four main groups of questions that philosophers of science raise about science. First of all, they raise questions about scientific methodology. How are experiments employed in order to test theories? What sort of errors are acceptable during scientific experimentation? What sort of evidence, or rather, what sort of observations count as sufficient evidence for a hypothesis to be considered as corroborated, for example? All these things have to do with scientific methodology. The second group of questions also has to do with the nature of scientific knowledge. This is related as well with how the importance of observation, how we observe and we experiment on nature in order to develop theories or change our views on how we understand certain phenomena. This is called epistemology in philosophy of science. And then we also have metaphysical questions. So metaphysical questions don't have to do with the nature of knowledge, so how scientific theories develop and are well justified, but rather with what those theories say about the world. So metaphysical questions have to do about the existence of unobservable things that are hypothesized in the sciences. So, for example, atoms and molecules, do they really exist? We don't see them directly with the naked eye. Our theories tell us that they exist. So philosophers ask questions about the nature of those things, for example, or how they relate to each other, what they tell us about causation, the causal relation between things in the world. And also the topic, which is very important in philosophy of science, has to do with ethical questions. How should we, or rather, how should scientists do science? What sort of ethical questions they should take into account when they're working in their field? Animal testing might be one of the most obvious examples of a ethical issue within this field, but also questions about AI, its appropriate use by scientists, the sort of scientific products, especially in chemistry. Chemists discover things that can be used as drugs, life-saving drugs, but also potentially, for example, as weapons. So these are things that come close to ethical issues, and that's where philosophers come in, pitch in, and try to be relevant and useful, I suppose. So that's the general field, philosophy of science. And then we have people who usually, though not necessarily, dedicate their work in a specific field or in a specific scientific discipline, rather. And we have a philosophy of physics, where people with a physics background usually work on. We have philosophy of biology. And also we have philosophy of chemistry, where people with some sort of chemical background usually, work on. And, the easy question of what philosophy of chemistry is, the easy answer rather, is that, philosophy of chemistry is just, we examine the questions and the issues that I just presented to you from philosophy of science by using case studies from chemistry. Right? And again, here we can track philosophical questions pertaining to chemistry being raised since very early. Even thinking about what the basic constituents of matter are is an ancient question, and we had many different theories since ancient times, and that's why I mentioned here Empedocles' four elements, for example. So everything is just a result of the combination of four things: water, air, earth, and fire. And there are questions about how they combine, what sort of properties matter, what sort of properties emerge by the combination of those things, right? We know now that this theory, of course, is false, but you can see that, questions that are philosophically relevant to chemistry were raised for a very long time. As a field, as like a formal, institutionally recognized field, philosophy of chemistry is even younger than its umbrella philosophy of science. It was officially created back in the 1990s. The official society is the International Society for the Philosophy of Chemistry, which organizes an annual conference, the conference of the ISPC, as we call it, where everyone from all over the world come together and present their work. And the main journal is Foundations of Chemistry, but there are also some online resources as well. One journal being Heil, I mention it here, Heil or Ili in Greek, if you like the kind of Greek flair to it, I suppose, which means matter. Now, I've decided to present to you what people do when they work on philosophy of chemistry by going through four main topics. Four topics that I consider, at least in my view, are some of the most representative things that people do when they study philosophy of chemistry. So let me start with the first topic. Hopefully, I will get your interest through each one of those. So the first one, chemists love the periodic table. Obviously, that's not a secret, I suppose. So it's inevitable that philosophers of chemistry would be interested in the periodic table as well. And there's a lot of work being done on the history of how the periodic table was developed. I suppose you might know Eric Sherry and his books on the history of the periodic table, right?
Yeah,
Have you heard
of a presentation about 5, 6, 7, it's a while, but yes.
Yeah. So he's also one of the founders of the society back in the 90s, and he's the editor-in-chief of Foundations of Chemistry. So he's a big figure in the field. And he has done a lot of work on the periodic table. And, when you look at the history of the periodic table, you find that, Mendeleev's version wasn't the one that was, uncontroversially accepted from the very beginning. It was presented by Mendeleev. In fact, there were disputes about between different classifications. And there were papers being published back in the 1800s about which classification is better and which one chemists should use. And three were actually the main candidates. One, of course, was Mendeleev's version of the periodic table, which classified the then known elements in terms of increasing atomic weight. But there was also Newland's version of the table, which, if I remember correctly, classified it in terms of a simple numerical relation. But I don't remember exactly on what that numerical relation was. But it doesn't matter. It was a different sort of classification, and then it was Meyer's classification as well. Now, what is interesting philosophically about this episode in the history of chemistry is that the dispute between the three classifications wasn't based just on empirical observations, in the sense that one of them was more accurate than the other. Rather, if you read the arguments that each of the chemists brought forward, their claims had to do about certain values that each one held to be more important, and that was satisfied by the proposed table. So, for example, Newlands would say, my table is better because the principle which underwrites that classification is a simple relation between certain properties. So it was simplicity that was the main value that Newlands took as important, right? Meyer's table, Meyer said, well, my table is better because it only accepted elements for which we have very accurate measurements, right, of atomic weights and other properties. And so accuracy was for him a more important value than simplicity. And then we had Mendeleev, who defended his classification on the grounds that it was more complete. So it would include more elements, more of the known elements at the time, right? And so there was a competition essentially between three values, what philosophers call epistemic values, between simplicity, numerical accuracy, and completeness. Now, it turns out, or at least some philosophers argue, that the reason that Mendeleev's table won over the others wasn't so much because chemists were convinced that completeness is more important to defend than accuracy and simplicity, but rather because it managed to do something that the other tables couldn't, which is to predict elements chemists hadn't imagined existed, right? So here we see that there is a fourth value that came in, epistemic value, which is the value of being able to produce novel predictions. Now, this is very interesting for philosophers because we see that this is something that we see throughout other episodes in the history of science as well. When there are disputes between competing classifications, hypotheses, or theories, often there is what we call an undetermination of theory by evidence. So it's not that an experiment can help us decide which hypothesis is more accurate. Rather, what it is that kind of leads us to choose one theory or one hypothesis or one classification in this case over another is that it adheres or it satisfies a value that scientists deem as important. So this is a huge topic in philosophy of chemistry and philosophy of science. And the periodic table is a representative example of Mendeleev's table, rather, of one of the most successful kind of classifications in science, which showed how, the value of novel predictions, being able to predict stuff that you didn't even imagine are out there, kind of leads you and helps you to pick one theory or this classification over competing ones. So that's one topic. Now let me take you to another historical episode. Do you want me to stop for questions on each after I finish with each one, or should I just continue?
We usually save them for the end, but I mean,
Because I don't want to.
maybe
Anybody has questions here?
feel free to continue.
Yes.
Yeah. Okay.
Yeah.
So that's one topic then, the periodic table. Now I'll take you even a little bit further back. The so-called chemical revolution. Do you know the chemical revolution and what period it refers to as chemists? Have you heard of the chemical revolution?
I haven't.
No. So the chemical revolution refers to that time in the history of chemistry when people abandoned the so-called phlogiston theory and accepted Lavoisier's theory of combustion and the existence of oxygen, right?
Yeah.
And it's called a revolution sometimes, but though not necessarily, of course. Rather, when people talk about this as a revolution, sometimes what they have in mind is also Thomas Kuhn's book on scientific revolutions. I don't know if you've heard that book. You must have heard about the paradigm shifts, surely, if you've seen the Big Bang Theory, right?
Yeah.
So these terms have been popularized by one of the most famous books in philosophy of science by Thomas Kuhn, which is called The Structure of Scientific Revolutions, where he brings forward this idea that, throughout the history of science, there are certain very important episodes of change where scientists change so deeply their views about the world, and they change so deeply their theories that what happens is not just a small amendment in their scientific theory, but that's what he calls a paradigm shift, right? And that's when a revolution, a scientific revolution happens, according to Kuhn. Now, one example Kuhn brings in order to support his view of how science progresses is this episode from chemistry, the so-called chemical revolution. So before Lavoisier and the discovery of oxygen, chemists believed in phlogiston. They believed that when combustion occurs, what actually happened, well, that they explained rather combustion in terms of the absorption and the release of a substance that they called phlogiston, right? And that when combustion occurs, a substance becomes dephlogisticated. Phlogiston comes out, and it goes it goes out basically, very crudely, right? Now, Lavoisier, what he did in the 18th century, then here is Lavoisier. He said that phlogiston doesn't exist. It's not a thing, and that's not how combustion works. Combustion has to do with oxygen, right? And this was a crucial thing in the history of chemistry because some people even say it was this episode that actually, led to the birth of modern chemistry, which I'm not sure whether it's actually true, but it doesn't matter. So this is a very interesting episode in the history of chemistry because it brings about important questions, for example, about how we test our theories and how we are led sometimes to abandon theories that we've used for a long, long time. So you might not have heard of phlogiston, and it might not be surprising for you now that phlogiston does not exist. But for many centuries, people actually thought that phlogiston exists in the same way and with the same kind of strength of belief that we have about the existence of hydrogen today, for example, right? So it was a very big change in chemistry and chemists' belief system. And so what philosophers often raise is, how do scientists get to change their minds? Or change their theories, or revise their hypotheses, so strongly when they have already developed a theory that they've used, successfully. Some could even say for such a long time, and they use the example of the chemical revolution in order to study this question. Of course, here also. Some philosophers have expressed a form of skepticism, or some might even say, a pessimistic attitude towards science, because they've noticed that, many times scientists have revised their views or realized that they have believed in things that turn out to be wrong. So if that happened in the past, how can we be sure that even the things that we believe today are not going to be revised in the future, right? So how certain can we be about the existence of hydrogen and oxygen, given that, we believe them as strongly as, fellow chemists believed in phlogiston, and phlogiston doesn't exist, right? So what I sketched now is the so-called pessimistic meta-inductive argument. And it is an argument that is developed by the so-called anti-realists in the philosophy of science. So people that have decided to be a little bit more skeptic about, how literally we can take our best current theories about the world, given, the study of history and how many times scientists have been wrong about their scientific theories. This also is strongly connected with how strongly we believe in the existence of the so-called unobservable entities. So, okay, I'm not going to deny philosophers can even debate about the existence of tables, so about stuff that they see with their eyes. But let's just put aside that. There's an interesting question about the things that we don't see directly with our senses. How sure can we be that these things exist, given that we see them indirectly by using instruments? And, the data we often get by the instruments, we have to interpret them using a background theory, right? So we make assumptions that our theories or hypotheses are correct, and based on those, we extract and interpret the data that a certain machine might produce, right? So even here already, given that everything is theory laden, that's also a term that is used in this topic, there is some skepticism about how strongly we can believe in the things that we don't observe directly. So that's another major topic where chemistry contributes.
So
Now I'm going to go to another favorite.
before
I
you
still
go,
have to, yeah.
before you go on, so I can't recall, this is about the chemical revolution.
Yeah.
I can't recall reading about it in that way, the chemical revolution. But in fact, he did revolutionize the science. And I think you mentioned that some people refer to it as the beginning of modern chemistry.
Yeah. Yes.
Right. And part of the importance of Lavoisier is that he measured things.
Yeah.
So he would take a metal, combust it, combine it with oxygen, weigh it before and after, and found, oh my God, and found, that there is a difference that could be associated with the addition of oxygen. So to me, that is part of that chemical revolution.
You're absolutely right.
Yeah.
Yes, I didn't mean to deny any of that. You're absolutely right. So that was the main, that was one of the main reasons that the crisis occurred with the phlogiston theory, because, according to the phlogiston theory, when combustion happens, the thing that remains after combustion has to weigh less.
Right.
But that didn't turn out to be always the case.
Yes.
And Lavoisier made this even harder, exactly for the reason that you said, that he provided very accurate results of that mismatch, right? And ways that they tried, if you study the history of phlogiston, you'll see that, and that didn't only happen with chemistry, that also happened, for example, with the Ptolemaic system. The phlogiston system started to, whereas at the beginning they had one theoretical framework where phlogiston explained, in a coherent way how combustion and other phenomena happened. Then because of these anomalies, sub-theories were created and many different phlogistic theories were proposed, each one trying in different ways to solve these anomalies. But then they couldn't anymore. And that's why Lavoisier was so important, because he said, you know what? None of these versions of the phlogiston theory works because there is no phlogiston, there's oxygen, right?
Exactly.
And I have exact measurements to show how oxygen explains much better combustion and other phenomena as well. So yes, you're absolutely right. I didn't mean to say anything that goes against what you said.
No, I just wanted to add that so that our students also understand that contribution that Lavoisier made to chemistry.
No, it's very important. It's just, and I had this discussion recently. Lavoisier was very important because he managed to do exactly that. But there are also other episodes which have been overlooked and which one could claim could also count as the birth of modern chemistry. For example, the turn from alchemy to chemistry by Boyle could also be marked as, the birth of modern chemistry. And actually, Boyle is sometimes referred to as the father of chemistry because of that.
Right. Yeah.
Right? So there is a small debate about if there is a point where you can say now chemistry was born, and which point that was.
Right.
Where you don't really, the other way you can just circumvent this question entirely is say, well, there's no unique starting point. There were certain episodes that were all equally important.
Yeah.
Creating modern chemistry. I think that's the most sensible way to do it. But there are many different interesting things that people, examine also with Lavoisier. There's also a lot of, especially in the history of chemistry, a lot of talk about the contributions of his wife, Mary Lavoisier, in his work. Apparently, she helped a lot in the experiments and correcting the works and the writings of Lavoisier. And this is also something that is being, illuminated in recent
years. That would be a great topic for another seminar.
Definitely, if you want, we can dedicate a whole seminar just to that.
Okay. I'll talk to you about it.
Okay. So should I go to the next one?
Yes,
Uh,
yes.
Whatever. If I have still 5 minutes, right? 5, 10 minutes. So
Yes.
another favorite concept in chemistry. I'm sure um, you know it. Is the chemical bond, right?
Mhm.
Now in philosophy, and this is something I've personally worked on as well. As I said to you before, in general, philosophers are interested in whether unobservable entities exist or not. And another example that is invoked from chemistry is the chemical bond. And here, actually, if you go into the history of how the chemical bond was developed, you'll find there was some sort of debate about whether the bond exists or not. And I have here two representative examples of this. First, I have Lewis, Gilbert Lewis. Everyone knows him, I'm sure. So he said at some point that in the mind of the organic chemist, the chemical bond is no mere abstraction. It is a definite physical reality as something that binds atom to atom. Now, of course, I cannot get into the mind of Lewis and tell you whether he had like a strong philosophical position in mind when he said that. But for a philosopher, this is a very heavy statement because it implies that he takes the chemical bond as being a real thing in the same way that we would consider, the table to exist, right? Now, a contrasting position was expressed by people that developed especially early models of quantum chemistry. And here I have Coulson, who worked on the valence bond theory, on the BB theory in quantum chemistry. And he said, a chemical bond is not a real thing. It does not exist. No one has ever seen it. No one ever can. It is a figment of our imagination. Now, this is an anti-realist position about the chemical bond. So as you see, it is inevitable for philosophers not to notice this and see whether there is any interesting point about the existence of the chemical bond or not. And this is not only something that philosophers, I think, are interested in. I found also more recent papers in the chemical literature. That's why I have this quote where it says later studies. Now I have your picture right in front of the quote, so I cannot read it. So, no, it's the whole thing. It's not. It's all the. But you can see the quote, can't you?
Yeah, we can see it.
We are seeing
Okay, I don't need to read it then because the window covers the quote, so I cannot read it. I'm sorry.
You should be able to
But
move
you
it.
can see what it says there. So there's still a question, I believe, in the chemical community about what the chemical bond is. And these are questions that are, at least to some extent, philosophical questions. And they have to do, as I say in the slide as well, questions about existence, whether there is a chemical bond in the same way that other tangible things in the world exist, but also questions about the precise nature of the bond. What is this thing? Is it a material thing that binds atoms? Does it just refer to a property of molecules or an energetic state? So does it refer just to the state where the entity becomes stable and we say, the things within it are bonded, right? That's called the energy. Robin Hendry, who's a very famous philosopher of chemistry, calls this the energetic conception of the chemical bond. Or is it just an abstraction, something that we made up in order to kind of convey certain properties of molecules, right? This is also another position one could take. So these are philosophical questions. And they also, something else that is very much related to the question of existence has also to do with composition. So the chemical bond, if it is a thing, it's going to be a chemical thing. How does it relate to the physical constituents of matter? So how is it composed of the subatomic particles and interactions that make up a molecule, right? So answering or addressing rather the question of existence in the case of the chemical bond is bound to lead you to questions about composition, how chemical things relate to physical things. And this brings me to the last major topic in the philosophy of chemistry, which has to do with the relation of chemistry with physics. A side note here, in the 1990s, when the philosophy of chemistry was officially created, a very big part of the literature within that field was occupied with examining the relation of chemistry with physics. And if you go to those early papers, you would actually notice that many authors, including Eric Sherry, for example, would say that we have to defend the autonomy of chemistry from physics, and we have, because this also will lead us to defend the autonomy of philosophy of chemistry from philosophy of science and philosophy of physics in particular. So there was a certain also kind of a stance in the field that, we need to this question is, and I'm using their words now, this is an existential question, how chemistry relates to physics. And of course, how the sciences relate to physics and fundamental physics in particular has been a question that was raised much earlier than the 1990s in the philosophy of science. And, when you go into this question, a picture which often circulates is this one here that I show you, the pyramid, right? Where you have fundamental physics as the basis and subatomic particles and their interactions. And then above that, we have the atoms and the molecules. And above that, we have the cells that are made up of atoms and molecules. And then we have individuals and then social groups and so on, right? And this picture is the so-called traditional reductionist picture of how nature is structured and how things really are composed of smaller things. And this is where also the question of chemistry's relation to physics comes in. So this is one of the biggest debates in the philosophy of chemistry, but also in philosophy of science. There are many different views that have been proposed, and there are also amendments to standard views. So in the beginning, so I'm going back to this picture. In the beginning, there was this idea that, if you are a reductionist, in the sense that, if you believe that everything is just the result of, the composition of physical stuff, there are only electrons and protons and neutrons, to put it like very crudely, and nothing else, then you would have to say that nothing else exists in the world, right? So in some sense, tables, cells, colors, consciousness, everything is just, different combinations of subatomic particles and how they interact. Complex combinations, but just combinations of those things, right? So this is called the eliminativist kind of version of reductionism, which has been mostly abandoned even by reductionists themselves. Right. So now it's more prominent, the view within the reductionist kind of field that, we still admit that everything in a very important sense is just the result of physical stuff. So there are no mysterious forces outside the main physical forces that physicists tell us exist. Nevertheless, in another sense, bigger stuff are also autonomous and distinct from the things that they are composed of. Right? So this is a different sort of reductionist version. But even these versions have been challenged, especially in the philosophy of chemistry. And an example that has been used by the so-called anti-reductionists, so people who don't believe in reductionism, in the reduction of chemistry to quantum physics, is molecular structure. So they've taken up this example and they've noticed that, when you they say, so the argument goes as follows. When you want to describe a molecule quantum mechanically, just by solving the Schrödinger equation, right? Taking into account the interactions of, all the neutrons and the protons and the electrons, then actually you cannot derive information about the structure of that entity without doing some approximations in the Schrödinger equation and making some background assumptions that you draw from chemistry. This fact is taken as evidence that therefore there is no reduction, that chemistry doesn't reduce to physics. Because you use information and knowledge from chemistry about the systems you examine physically, This means that it cannot just be the result of, physical stuff. It emerges. That's one way that they characterize it. Molecular structure emerges in a different level from the physical level from which the molecule is composed. So this is a huge debate in philosophy of chemistry. People work a lot on molecular structure in particular, trying to understand whether the Schrödinger equation can give you information about the structure of molecules without using prior information from chemistry, and whether even this argument suffices to be an anti-reductionist or not. This was also my PhD thesis. So I've been working on this for 4 years. So this is something you can work for 4 years and not get an answer at the end. Or at least you can get some answers, but not the whole picture, perhaps. So this is a major topic as well in philosophy of chemistry. And molecular structure is a major case study in this. Now, of course, I've just scratched the surface. There are also many other topics in philosophy of chemistry, but also topics that haven't been addressed in the field, but that could be very interesting philosophically. There are there's a feminist philosophy of science, so the role of women in chemistry, how they've contributed to the field, which might have been forgotten or neglected. So this has to do with feminist issues in philosophy of chemistry. Of course, AI, how and whether it contributes to genuine chemical progress is another philosophical question. AI supposedly allows us to make, predictions and explanations of chemical phenomena. But does it do that in truly novel ways? What sort of errors might be produced by using AI? These are questions, novel questions that haven't been addressed yet and that are very interesting. Also, the use of idealizations and models in chemistry. How literal can we take models? We know that they are very important, especially in chemical education and in understanding chemical phenomena. But even chemists themselves very often know that models in some sense are strictly false. So how important is to acknowledge that, not only among ourselves, but also when we teach chemistry. So this also has to do with chemical education. The nature of chemical explanations. This is also a topic in philosophy of chemistry. Here, the case study that is usually invoked when we think about explanations in chemistry are reaction mechanisms. How do they manage to explain chemical reactions and what sort of explanations they give? So many, many more topics in philosophy of chemistry. I'm happy to give you more details if you're curious. So that's it. I've put some references here. I've put my website. I've put Jargonium's website, which is, all us early career researchers write, short articles about our work. And I've also have 2 recommendations. So if you want a starter on philosophy of science, I recommend a book, which is, a classic book that the first year undergrad students usually start with when they go into philosophy of science. And then, unfortunately, we don't have a starter book in the same way in philosophy of chemistry yet. So I recommend the entry from the Stanford Encyclopedia of Philosophy, which is an online encyclopedia. If you just Google philosophy of chemistry Stanford, you will find it. Yeah, thanks.
Let's thank our speaker. So we start questions and I'll jump ahead because I get the hot seat and I get to ask questions first. I have a long list, but I'll just ask one. So how would you say communication and science play a role in the study of the philosophy of chemistry, right? You mentioned a lot about take the periodic table where people are publishing results and saying, hey, mine's better because, etc., right? How important do you think the level of communication that those people, the scientists have to explain their philosophy of choice is?
So it's what is important is not necessarily to study the philosophy that might underlie, the philosophical views that chemists might have about a specific issue, but even how they work. So indeed, in the case of the periodic table, we see that, chemists had a sort of philosophical exchange. But sometimes, often that doesn't happen, or it is very implicit, and people, and even scientists themselves might not realize that they're having a philosophical debate, or that their views are based on some implicit philosophical assumptions. But that doesn't matter so much for philosophers. They study the articles or the disputes, the sort of experiments they use, even what sort of errors scientists find acceptable in a certain experimentation is a form of evidence when they analyze philosophically, a specific science. And it's a little bit, it's also tricky. It's a very good question that you raised, because sometimes it's tricky to rely too much upon the philosophical views that scientists might have about their field, because those views might be based on ideas that, or on concepts that chemists or scientists do not understand the same way as philosophers do. So, for example, when Coulson says the chemical bond does not exist, it's a mere abstraction. What he says or rather, Lewis. I'll use Lewis. It's better when Lewis says it's a real thing. We cannot say for certain whether what he means by real is the same as what philosophers mean by real, right? So real is defined usually by philosophy as, something is real if it exists and it is mind independent. So its existence does not depend on how I conceive it, right? So in that sense, it is real. For example, money is not real because we've invented it, right? It exists as a material thing, but the value we assign on money is something that we've all agreed upon.
Yeah.
And if we were to disappear, $5 wouldn't have. The value wouldn't exist in the same way they exist now, right? Does that make sense?
Yeah.
So you see there is a nuance behind the term reality and existence that might not necessarily exist, behind the concept when it is used by scientists. Or they might have a different sort of concept in mind, right? So it can be a bit misleading when you analyze their views to kind of stick, or rather put too much. You cannot put too much weight on how scientists themselves kind of express philosophical claims, I suppose.
So I also have a couple of questions, but just a remark on the question that Ian wrote. Ian asked. It reminded me of a statement that's attributed to Native Americans, which says, "Those who tell the stories rule the world." Have you heard that before?
Yeah, I've heard that.
Those who tell the stories rule the world. And there's a lot of truth to that too. Anyway, yeah, you could think about that one.
Yeah.
So that's actually, there is a philosopher and historian of chemistry at the University of Cambridge, Ha-Seok Chang, who is kind of an advocate of this quote that of this idea. He has written about the chemical revolution and about phlogiston, and he has argued that actually, we should pay more attention on phlogiston. And, if we were to develop again this research program, we might learn things that we don't know, right? And it is because, the people that Lavoisier won, that we have only the winners side of the story, I suppose. He kind of promotes in a very more general sense what you have just expressed. Yeah, that's also a stance, I suppose.
So I have two questions. The first one is, do you then believe that we are all wave functions? It's
Oh,
meant to be provocative, but whatever. I mean, some people actually do believe all of reality is just wave functions.
well,
In fact,
I will
just
go back to,
read
yeah.
someone saying that the whole universe is just we are living inside of an electron.
Oh, okay. And what is it? Should I answer this one, or will you ask me?
I
Will you
can
wait?
ask a different question.
No,
So,
so I can answer
okay,
that one first if you want. So,
okay,
so what you said is what the eliminativist reductionist would say,
right,
right?
right.
Um, but you don't need to be an eliminativist in the depressing way that we are just wave functions and nothing else. And you can still stick to being a reductionist in an important sense. And I think we should be. So I would put myself in the reductionist camp without being an eliminativist. So yes, we are just physical stuff in some sense, but that doesn't mean that, physical stuff don't combine in very complicated and fascinating ways and create things that are um, distinct from just being mere aggregates. I would put it this way: we're not just mere aggregates. We're not just a puzzle of small pieces and nothing else. The puzzle is actually it exists as something over and above the pieces that makes it up.
Hmm.
But still, it's only the pieces. There's nothing mysterious beyond that. So that's the reductionist flair.
But this leads to my next question. How do reductionists explain water? Because we take hydrogen, we take oxygen, both gases, we end up with a liquid at room temperature.
Yeah.
Oxygen supports combustion, is essential for combustion. Hydrogen supports it. Water basically is the reverse. It quenches it. And if we didn't know anything about those three substances, we would
Mm,
not have been able to predict the properties of water
yeah.
based on the knowledge we had of hydrogen and oxygen. So how do reductionists explain how new properties, new, functions and all of that comes from even the periodic table, right?
Yeah.
You look at hydrogen is a gas, next helium is a gas, and then you hit lithium, boom, you have a solid.
Yeah.
Could you have predicted that?
Mhm. Yes. So you've touched upon another major topic in philosophy. You have a very good eye for the right and the difficult questions, which has to do basically, um, how to when we combine things, into aggregates, they seem to lose the properties that they had as individuals. Right? That's the issue here with water. So you put hydrogen and oxygen, and when they're put together, hydrogen and oxygen no longer exhibit the properties that they had on their own. Does that mean that hydrogen and oxygen are not there in water? Is something else there? They are combined. It doesn't seem that they are substituted by something else, by a completely different element, right? But nevertheless, the properties that they had on their own have disappeared now that they've come together. And this is a question that goes back to ancient times, but a part of the answer to that has to do with identifying, there are two different categories of properties that things have, the so-called intrinsic and relational properties. And you don't need to think of chemistry to kind of see how the different properties, whether they're intrinsic or relational, are instantiated under different circumstances, and they're not necessarily exhibited all the time. So, for example, I am. Let's assume that I am a very chatty and friendly person, right? That these are properties that I have. If I were to grow up in a room by myself where I see no one and I speak to no one, I will never instantiate those properties. It is as if I don't have them. It is only when I relate to other people that I realize those properties, right? And conversely, I have certain properties that I exhibit by myself when I am in the room somewhere and I don't know, imagine whatever you like, which I do not instantiate when I'm around other people, right? So it's the same, you could say more or less the same thing with water. So hydrogen and oxygen exhibit certain properties on their own, which they might not exhibit when they interact with each other because they cancel each other out. Even that, I might say I have the property of being chatty when I speak to you, Desmond, but when I speak with my mother, I don't want to say a word because she says something that I don't like listening, for example, right? So I have a completely different character there. So it also depends with who you interact, what sort of properties you have. So here, this is a metaphysical question about the nature of properties, what sort of properties things have, and under what circumstances they realize them, and whether the realization of a certain group of properties is what makes the thing what it is, or it is something that just makes part of the identity of that thing. I fell into a very complicated issue, I have to tell.
If we go in even further on water, right?
Yeah.
Going further on water, that sort of builds on what you just said about relational.
Yeah.
A single molecule of water does not have a boiling point.
No, it doesn't. So, right, the property can be assigned.
Exactly. It's only when it's in interaction with other water molecules in bulk
Exactly.
that you do have the phenomenon of boiling point. So
Yeah.
idea of relational is another way of saying it is interaction. I mean, for example, for water to have a boiling point, there has to be hydrogen bonds being broken. But with a single water molecule, there are no hydrogen bonds to break. So therefore, there is no boiling.
Yeah.
Yeah. So even,
And also,
yeah.
this also it also has to do with scale and how many molecules you have.
Right.
So there's also a famous paper by Julia Burston, who has written about gold. And depending on the scale, so at the nanoscale, gold has different properties than at a larger scale if you put more and more atoms of gold together, right? So even the amount of molecules that are concentrated or the scale at which they are found makes a difference to the properties they're going to exhibit. That's a very
question. We have a question.
Yeah, I was gonna say, do you think philosophy has more of a role in chemistry today than back when chemistry was first starting off?
Did you hear the question?
For chemists back then, you mean? If it had
Philosophy,
They had more.
I think philosophical questions cropped up in the past for chemistry too. And they were important, I think, in a sense. I suppose now they are more important because, especially the last 100 years, the things that we have produced by developing chemistry have a very strong impact on our everyday life in a way that they might not have had 300 years ago. Though that's not entirely true because, all the things that we've developed, I would venture to say most of them are the product of chemical phenomena, of chemical reactions, right? The food, the beer, the wine that they made 2,000 years ago is the result of chemical processes, no? But still, you could say that, now we have so many drugs that have the capability of saving so many people's lives, and we can create vaccines and discover new drugs and make weapons in a way that, so chemistry can be influential and in a way that it wasn't 400 years ago. So if that's the case, then philosophy becomes more pertinent and important as well.
Well, we'd like to thank you one more time.
Thank you.
Is it
I think there's a
possible for me to jump in with a question?
Yeah.
Oh, go ahead.
Go for it.
This tags on to what you were just talking about as well. It seems to me that well, first of all, I just want to say I really appreciated your presentation. I'm retired, 65-year-old, spent 32 years as a chemist at Dow Chemical Company, and I'm interested that you're doing all this philosophy and now you're studying chemical engineering. So that's intriguing in its own right. But just like you're moving into the practical or pragmatic side now, perhaps.
It's the other way
But
around.
in terms of the other way around. I thought you were doing. Did I misread your bio? I thought you were doing the engineering now.
No, I did chemical engineering as an undergrad, and then I switched to philosophy.
Oh, okay. I got it backwards. Okay, very good. Well, I guess the question is, as I observe society over these years, it seems to me that the more political a scientific subject becomes, in other words, the greater the public impact or the policy impact of a topic.
Yeah.
It seems to me the more ossified science becomes, certainly as it's discussed within the political sphere. In the COVID era, we've heard the term "the science," of course, bandied about by various people. This idea that there's one kind of scientific paradigm and that's the truth, and we're going to, shun anybody who disagrees with that. That could apply to all the hot topics of today. And I remember as those topics were developing within the scientific literature, a great deal of debate by scientists on various points of view. But as it rose to the level of sort of public consciousness, it became solidified around one particular perspective. And then even within the scientific community, then dissidents were viewed as outcasts. They no longer could be published, etc. What does the philosophy of science, and in particular, since some of these topics are very chemistry related, I'm curious, what is the public impact of philosophers of chemistry today within the public sphere? Are you being heard? Is it too new a field to have that kind of impact? I mean, again, I'm 32 years in the industry, and this is my first time to hear specifically, philosophy of chemistry. I've heard, of course, of philosophy of science, but so this is intriguing to me. But I'm curious what kind of public impact you're having.
Yeah, that's a good question. So in general, I would say that philosophers are first, you have to look at philosophy of science more generally. And unfortunately, philosophers of science in general, whether it's chemistry, physics, or just, plain science, have a lot of trouble of getting out their ideas. And there are some, through the societies and the associations, we also have some training on how to write popular science articles, how to pitch, articles to big magazines or, newspapers and stuff like that, create podcasts. So there is a kind of urge now, especially from my generation onwards, in general in philosophy of science, to try and get out philosophical ideas. Now, philosophy of chemistry, because it's a very small fraction of philosophy of science, has an even harder time doing that, because we're very few people, I have to tell you. I don't think we're more 50, 100. I think I could say safely that I know that the big names. It's not very hard to find to track the entire literature in philosophy of chemistry. Imagine we don't even have a monograph of what is philosophy of chemistry. We have books that are collections of articles, academic articles, but we don't have like a starter. What is philosophy of chemistry? So that already is indicative of the difficulty. We're one step behind in that sense. Though I agree, it's very important to get that through. And that's why we've created also, so Jargonium, for example, has been an effort towards that. to showcase kind of how philosophy can be important to chemistry.
So one of the comments I would make on this too is that I think a lot of people in the public know the name Neil deGrasse Tyson.
Yeah.
We don't have that in chemistry.
No, we don't.
Okay.
No.
We don't have that definitely in philosophy of science. And so to answer some of his points, then if we had that sort of like communicator of chemistry, of chemistry ideas, of chemistry philosophy on that level, then we might start to see people really taking a more enlightened approach to how chemistry and science operates. I mean, the fundamental thing is, you know, theories are made, hypotheses are made, and they are challenged every single day within the scientific community. But in the public view, some of them feel like what Robert was saying is like, it's just one view, unchanging, and people, you know, live or die based on that. That's not the
Right.
actual, you know, description of what actually happens in science. It's the back and forth, the dynamism of research, of going after, you know, different hypotheses and so on. So that's a need. And hopefully you might be able to bring a monogram on
I want, you know, but even if I tell you the difficulty of getting a book out, of even writing it and getting it published.
Right.
But you know, there are also, you know, practical difficulties because there are no philosophy of chemistry positions. So I cannot be, if I want to get a job at the university, at the philosophy department, there's no position philosophy of chemistry.
Right.
There's a philosophy of science or a philosophy of physics, which means I'm going to compete with people who are doing another science, perhaps, or just science in general, right? So that already makes it difficult for pure philosophers of chemistry to survive, to have kind of jobs that will sustain them professionally.
Right.
But you know, a way that chemists perhaps could help, and for example, we have this in Greece. There are some master programs in Athens. For example, I teach at the chemistry department, philosophy of science. There's a master program in chemical education, and they have a course, Introduction to Philosophy of Science. Now, I don't see them hiring me, you know, permanently, but in principle, you know, we could create positions within the science departments for philosophers, perhaps.
All right.
Is there time for one more question?
Make it short and make the answer short.
I'm sorry, because this is a big one. I'll throw it out there and you can make your answer short if you wish. But in response to two of the things that you said today, I just kind of jotted down a couple notes. The first one really was when you made in one of your earlier slides, you made the comment about the belief in the existence of unobservable entities, and that rose in my mind, of course, the question of how that differs from the God questions. Essentially, the argument of the Discovery Institute, for example, in Seattle, which is a intelligent design kind of organization, their philosophers argue that science needs to remove the assumption of methodological naturalism and be open, essentially, to the supernatural. The other thing that you said in one of your last slides, you talked about emergence. And I think in essence, what you're saying is that it's the combination of, as opposed to reductionism, that emergence is essentially the combination of the physical with information. And that's essentially the argument that the intelligent design people make with respect to, you know, the molecules of life and so on, that it's not just molecules, it's the information, in this case, you know, contained within DNA and so forth, that's critical. So I'm curious what your thoughts are on the big question and in terms of how philosophy of chemistry, what that brings to bear to that question.
I cannot give you a short answer, I'm afraid.
I knew
It
that.
is a big question.
I don't
And
have, and you know,
just so you know, we have lost all of our students. I am the
okay.
only one in the room now, so just to give you that
Well,
context.
I can just say that you know, these are very existential questions, and actually,
Yeah.
the reductionist debate hinges on, you know, one's existential stance,
Mhm.
and so I don't know what to say about that.
I know it's a big question.
It is,
Yeah.
yes, it is a very big question. I don't know. I'm sorry, I don't know how to the you know, in the so there are two traditions in philosophy. There's the analytic tradition and the continental one. And in the analytic tradition, we tend to cut problems into pieces like scientists do and look at the evidence, the empirical evidence only. So that's the naturalized kind of way of doing things. And so I'm not very accustomed with dealing with existential questions, exactly because I've compartmentalized these things into different kind of boxes. And so I don't have a very well researched or nuanced answer to give you. But
But
you're spot
I
on that these are relevant issues.
but I
Well,
will
you've touched on two concepts that very much are in the certainly on the radar of Discovery Institute. So
Yeah,
it's
definitely.
intriguing.
But you know, there's a way to kind of we compartmentalize these questions often by limiting to certain cases. So I'm just going into chemistry and physics, and I don't look beyond that.
yeah.
And sometimes you can say even if there's emergence in that level, that doesn't mean that there is emergence beyond that as well,
Right.
Right.
right? So you can just make local claims, and I prefer making local claims because it's harder to make larger than that.
I mean, if philosophers question the existence of a table, I mean, please, you know, if we are talking about existence
You know, if
of
you go
God,
into the
things that we cannot see, that definitely is at a deeper, higher level.
yeah,
So I will definitely be contacting you again
please,
about the possibility of doing a talk on the contributions of Lavoisier's wife. I have never heard that before.
okay.
So that would be a really interesting one that, you know, talks about the role. It could be placed in the role of women in chemistry. But yeah, this one would be really, really good.
I'd love to. I actually teach feminist philosophy of science, so
Okay.
I can even do a small introduction to what kind of issues we raise with respect to science.
Okay.
You
I'll
can
be
do.
calling on you again.
Please do. I love doing stuff like that. And if you have any comments or feedback, things that
Yeah.
I could improve, just let me know for next time.
Yeah. So one thing that you and I could talk about later is how do we teach emergence
Oh,
in chemistry? Because the examples that I gave is examples that, to me anyway, are anti-reductionist. Number one, and number two, they really, the idea of emergence is not cross-disciplinary, multidisciplinary. I mean, the very picture that you showed when you talked about molecular structure, I didn't think in terms of reductionism. I thought in terms of emergence, because at every different level, something new emerges.
yeah.
Right. So anyway, I would love to have ongoing
I will send you some.
conversations.
I can send you some references if you like, some
Okay.
papers.
All right. Sounds
Okay.
good.
Okay. Let's stay in touch then.
Okay. Appreciate you.
One
Thank you so much.
one final question that's easy to answer. If I go to your website that I jotted down, is there a link to your dissertation anywhere? Because it sounds like it would be an
Yes,
interesting read.
if you go to the tab publications,
Okay,
right at the bottom,
great.
the
Thank you so much.
publication.
Enjoyed it.
Thank you. That was wonderful. I really enjoyed it. Thank
All
you.
right.
Thank
Take
you, Dr.
care.
Mary.
How late is it there now?
Oh, here, what time is it?
Yeah.
It's 12:30. Well,
Oh my
12:40.
God.
Yes,
Thank
I
you.
am tired. I want to go to bed now.
Thank you so much.
And
Thank
you know,
you. All
I
right.
have
Take
I have
care.
I will talk to you next time.
Okay. Thank you. Take
Bye.
care. All right. Bye-bye. Bye. Okay.
Very interesting talk.
I know. I know.